of the workshop is Greg Wayne from Columbia. He's talking about an integrated cognitive architecture.
I'm actually a DeepMind. I don't know how it got mislabeled as Columbia.
Okay, I'm going to put Columbia on my copy.
Well, cool. Thank you for staying to the bitter end. I'm going to be talking about some work that's taken a pretty long time, actually, trying to unify a lot of ideas in machine learning. So even at this meeting, it was a really nice talk by David Cox about predictive coding models. You had Matt Botvinnik and Collins, XJ Wong, talk about the relationship between working memory and reinforcement learning. Surya talked about state estimation and navigation. But I think that these tend to be studied in isolation. And we maybe would profit from studying them together. That would force us also to think about how these things should interact. That's non-trivial. Also, when you study them together, more is different. Maybe there are constraints given by one process that inform how the other process should actually work. So this, I think, is both a strategy for us to understand really what the functional capacities of these systems really need to be, and also gives us working technology at the end of the day. So I'm going to talk about some work I've been doing for some years on neural networks with external memory to start off. And then how I migrated from working those networks with external memory to work on reinforcement learning with neural networks with external memory. Actually, I found that to some extent disappointing. So we'll get to that disappointment, but then we'll get to, I think, an honest resolution to some extent, which is an agent model called MERLIN, or the Memory Inference and Reinforcement Learning Agent. So we at DeepMind tend to build tasks and have agents perform tasks. So I'll show you this thing working on tasks in virtual reality that are often characterized by partial observability. So all of the information relevant to the agent's performance is not present in its sensors. Therefore, you need to have memory to remember the things that are needed to make decisions at the given moment. So I started off working with Alex Graves and Ivo Danihelka on systems that have that are like conventional neural networks, or at least very much so now, long short-term memories, but augmenting them with memory systems. So I think what Les talked about with allocation being a primitive is something that resonates with me. So this is a system, for example, that takes in an input and is a conventional recurrent network, but it has extra output channels that can influence another system altogether. And that other system is just a big matrix with rows. So I don't know, we iterated on this thing and it changed over time. I'll just give you sort of like the platonic, the simplest one of these systems. So we first called it the neural Turing machine, and then we called it the differentiable neural computer. But whatever it is, it's this matrix plus this LSTM. And it can do a few things. It can write at every time step, so this works in discrete time. And that writing process is very simple. It just allocates to a new row. And reading is also pretty simple, and I'll express that in a moment. You can train these networks by backpropagation methods, and they can learn to recruit this external memory. And what's kind of cool about them is that they can do simple kinds of algorithms with memory. So they can do things like looping. They can do process data structures like graphs, and they have higher capacity memory than the sort of the simple recurrent networks and the LSTMs. So the NTMs were just the sort of earlier, more kludgy version of the DNCs. Okay, so how do they work? You have to define the mechanism of access memory. So for example, reading is a little bit simpler than writing, or actually it used to be the case, but now it's actually maybe writing's more simpler than reading. You have something called the read key, which is just a vector put out by the LSTM. So it's an extra output channel that's initially random vector. So it's a linear mapping from the network dynamics to a space of a given dimensionality. That dimensionality is the same as the size of the length of a row. And you do a dot product against every row entry. And that gives you a similarity measure. Okay. And so it's k times mti. So that's the ith row's values at time t. Okay. And that gives you exponentiate that and make a distribution that I called a weighting to keep it distinct from the notion of weights in a neural network, because this is a dynamically produced quantity. And we called it attention because, well, it seems a little bit like a kind of gating mechanism, and because everybody else wanted to call it that too. So this gives you a way of searching memory by putting a key and then getting a distribution over the rows of memory. And then you can average the rows of memory, have a weighted average of the rows of memory, and pull out an average value, a weighted average, m. So that's the reading mechanism, basically. And this is all differentiable. So the attention weighting is a smooth function of all of the inputs in the network dynamics. Cool. All right, so at every time step, this system is putting out a read key and getting out read values. And you can actually have multiple read heads, we called them. So you can put out several read keys and in parallel look at different things in memory. Cool. All right, so writing to memory was at the time complicated, but now it's pretty simple. So we just, at every time step, we take the next row that's not written to yet. So we're typically dealing with sort of infinite memories. And you can fix that in various ways, but just for the time being, let's effectively consider this as infinite, or as large as it needs to be, like a Turing tape. And there's a vector put out by this LSTM as well, which is also the same size as the row length. And it's just inserted directly into the empty slot.
So there's no checking to see that the value is already there?
So it's empty, it's zeros before, in this case, that would be 0 initially, and then you're putting in this value. And you just write in row order. So you write, this is the fourth time step in the simulation, and you're writing to the fourth row. Cool.
I think he meant that vector already somewhere above in the memory.
Oh, no, you don't do that. So if you're writing the same thing redundantly, it just does it. We worked more recently on a system that, actually based on Pentti Kanerva's work, that if it were to write the same thing twice, would not write anything at all. It's sort of, but yeah, this one writes redundantly.
The read key is like infinite measure?
Now the read key itself is just the length of the row, sort of, let's call it that the code size, say. So it's, yeah, just so maybe we'll work with 200-dimensional vectors. So the key itself is 200-dimensional, and it's dotted against every row, which is 200-dimensional. And you have n of these rows. Maybe your simulation is 5,000 steps. You'll have 5,000 rows in the matrix.
So you're basically addressing by content. You don't have a separate address.
That is content-based addressing, which is a good idea. OK, cool. So anyway, D is also the same dimensionality. OK, in this model, D is learned. So it's learned based on some kind of loss function. So here was the simplest thing we ever tried, which was a loop problem. So on the left-hand side, you're going to get some inputs, which are just random bit vectors in time. And you'll see them for some amount of time until some sort of flag comes, which says, now you're done seeing it. Just repeat this now like 10 times. And there's another flag which says how many times to repeat it. So on the right-hand side is the output of the system, which is going to be a copy of this pattern. And in the middle, you have the memory, which is going to be written to by a write system, row by row, for a while. And this is, again, the NTM, which is more primitive, so you can actually see it writing to multiple locations if you look closely. So kind of ignore that weirdness. But otherwise, it will kind of write one by one every pattern, and then it will read them through one by one. You'll see it pretty dramatically. This is what it does. It's writing. This is literal. This is actually true. This is what we literally, it's just a colorization of it. So this reading out is now going row by row down and checking all the patterns. And it's repeating that some number of times, and then it stops. Okay. And the important thing was that the LSTM network couldn't do this. So how do you build such a system? Well, you train it through backpropagation through time, at least at the present state of our technologies. So at every time step, you get an input x, and you produce some hidden state or recurrent state h, which includes the memory in this case, and all of the recurrent LSTM network. And you produce an output y, and then you, at the next time step, inherit some of your state from the previous recurrent dynamics from h1 going to h2, but also you get a new input and so on. So that's what unrolling this graph is like. And then you get an error signal and you backpropagate through this whole chain. So you store the whole system's sort of whole entire trajectory, which is absurd, but it is what we do. Okay. So then you optimize every parameter in this model to make those target values y hat more likely.
When you backpropagate, can you alter the memory?
You do not alter the memory, but you alter the parameters that influence the memory, so that the next time around you'll write different things to memory. Okay. So after that copy problem, we tried other problems, and that was just the simplest example. And I don't want to go too much into this particular model, but the next thing we looked at was data structure learning. So we represented graphs, random graphs. We would generate random graphs. In this case, it's a random planar graph. And we would represent edges on this graph as source nodes, edge labels, and destination labels. And those will all be numbers. So every label has a name, which is a number between 0 and 999, for example. And that would be represented just as one-odd inputs into the model. So you'd get a vector input at every time step, which says the source, the edge, and the destination. So that would describe one graph edge. And then across time, you describe the whole of the graph. And then you ask it to answer questions. So this is an untrained example, which we applied it to. This was the tube. And what this problem is the traversal problem, we called it. So it's basically from Victoria Station, go north on the Victoria line. So after you've described the entire graph, go north on the Victoria line, and the model should tell you where you get. Then go north on the Victoria line a second time. Where do you get? What's the node there? You go east on the Central line, and so on. So it should be able to fill in all the stations along the way. And the way it solves the problem is these are the locations in memory that are written one by one. This is the writing, and it writes to cross time. I guess time is running left to right here. It writes to location 1, location 2, location 3, and so on, all of these edges. And then when the query comes in, which is of the form, it's coded, I wish I had a laser pointer. It's coded right here. It says Victoria space Victoria North. So it's saying Victoria is connected to what when you go north on that line. It happens to be the station and the station line are the same. And then it does some reads of memory that are content-based. And it's clever how it does it. So what it learned was this. It produces, the LSTM controller produces read keys, right? And these read keys, actually, they're abstract and distributed representations, but you can decode them to those numbers 0 through 999. And then you can say what they mean in your encoding. And there's a from, a to, and a line. And the from in the read key is the station you've asked for, Victoria Station. The line you can decode, and it's exactly the line, Victoria line north. But the read key that the system has decided to use is empty or undecodable in the the destination. And then it looks up memory, and it finds the thing that has high dot product against this read vector. And it gets a vector back, which is the average of all of those rows, which happens to have filled back in the answer. And then it does that iteratively, going through the entire traversal of the graph. So that's how this system learns to do content-based lookup. Okay. So that's how supervised learning works too. So you train it on, you give it examples of graphs, and then you ask it questions, and you make it give the answers as you try to make them more likely. You could also do reinforcement learning with such a system, which I did and I found disappointing, but I'll get to that story. So here you have a policy which produces the action probability. So you have some buttons, and you have a random multinomial distribution over those buttons at every time. So A1 is sampled from pi of A1 given the state H and so on. And then the goal of the system, which is what policy gradient algorithms do, is to maximize the return from a given time point. So the sum of future rewards. And the way you do this is you backpropagate in the same way this quantity, which is the return effectively, and there are ways of making this work a little bit better, but it's the return from a time t times the gradient of the log probability of that action probability, just action distribution. So make more likely things that are correlated with return or reward. Okay? So that's the policy gradient algorithms. Now, I wanted to apply it to problems that seemed like they involved memory. Here's a simple example, the game memory. We built a little board of MNIST digits, and the agent sees a visual input at every time, which is right now in the upper left-hand corner with this 2. And it's going to bobble around, and then it's going to have to remember where it last saw the same digit. So it needs to remember what is where to solve this task. Okay? It's a kind of state estimation. That's the connection to partial observability in memory. All right, cool. So this didn't work very well, and I'll get to it in a second. So let's consider some architectures that we'll use to solve this task. Forget this, but this is an LSTM with a lot of extra gunk. So we're going to apply this to virtual reality experiments in a minute. So there's a lot of extra sensory data. But for this problem, you basically have to know that there's an indication of an image that is coming into the model. And there's your last action, which is coming in. So you know your choice is to go to 1 of 16 squares, and you know where you went last time, and you know what you saw. Okay, so that's coming into O, the observation, which is encoded by a system like convnets and so on. And then that goes into an LSTM, which is H, this recurrent thing over here. These dots mean there's a recurrence to the next time step of the simulation. So it's a time delay. And then there's a little multi-layer network that takes in both the memory state and the embedding that you get from encoding the stimulus. And then you produce this action probability distribution, the policy, and sample and action. So that's this sort of standard model, if you like. So that's like what Matt Botvinnik showed the other day. Then you can take a DNC, or a neural Turing machine, or whatever you want to call it, or just RL-MEM, which now has an external memory system. So it's the same deal. It's going to get sensory data. It's going to get an observation and encode that observation. And then it's going to interact with this LSTM loop over here, which itself gets to talk to a big memory by writing a write vector into the memory, by doing content-based lookup with search keys, and getting return values back out. Okay. So that's that system. We tried that, and those models do not work very well. Kind of mystifying. So the LSTM doesn't work for good reason. It doesn't have the capacity to store a lot of these images and their locations. So this sort of binding of location and image and doing it for many of them at the same time is difficult for the LSTM. You know, it's getting there at some point, but it's incredibly slow. It's painful. So I think if we ran this for like the, months or something like that, it might get there, but who wants to do that? Okay, so the memory system actually paradoxically does worse here. You'll see it do better later, so it's not like it's not a working system. But it's really not, it kind of could work, but it just doesn't have the right objective function is what we're gonna argue. So a score on this of 8 is solving the task, and this model, MERLIN, which we'll get to in a little bit, solves this entirely. But we'll see how. So I say it seems like the objective function is wrong on these memory systems. So the policy gradients, which you use, you randomly jiggle around and you get reward, are noisy estimators of anything. The gradient of the parameter gradient with respect to the loss, the gradient of the loss with respect to the parameters is noisy. Depends on the trajectory. So if there's like no reward in the environment, you learn nothing, for example. You get nothing at all. So you only get like chance events that are pretty rare events are the things that drive learning. But I think more importantly, it's like I don't even care about an argument about the mathematics because it feels wrong also. So they only learn to remember things based on trial and error, which is absurd. So this task is a perceptual memory task. You need to remember what you saw. That's something that your visual system needs to be participating in. And it should have nothing to do with what your motor twitches do at the end of the line. So there's something wrong with end-to-end learning where you care about the action probabilities driving your memory and the development of what representations you put into memory. So that's sort of the thesis. That is wrong. Okay. But I said to you, we're going to try to bring things together. And that's what we're going to do to fix things. So instead of using reinforcement learning with random trial and error to build the representations that we put into memory, we're going to just do unsupervised compression and prediction to do it, which is, I think, the kind of thing that like Jeff Hawkins has been talking about for a long time and other people at the meeting. Okay, so basically we're just going to do predictive modeling. So that's this paper. It's just on arXiv. If you want to see this, it's a long report of our studies. And I want to credit Alden Hung and Tim Lillicrap, who is just here, for being my primary collaborators on this. So you could do a lot of methods for you could use a lot of methods for unsupervised learning, and we just happen to choose a convenient modern one that we're good at. So basically, you can think of most of what we're doing as building autoencoders, but we happen to use these variational autoencoders. So the variational autoencoders are systems to build generative models. So at least most of the people who build variational autoencoders somehow care about building a generative model at the end of the day, which means they can sample from a distribution that they have control over, like a Gaussian distribution in high dimensions, a 100-dimensional Gaussian distribution, and then they can produce something that is cool, like an image that's like their data set. So that's, that initial sample comes from something called a prior distribution, and then you produce a variable z called the latent variable, and then you push that through a kind of a decoder, which says what's the probability of an image given z, or it gives you basically an image. Okay. But the way you train this model is you plug in a lot of actual images, x, and you produce an encoding of them into the same space, the same probability space for z, based on x. by a neural network. And then you say, okay, I really want my distribution here, Q, which is a kind of a Gaussian distribution in this space of the latent variable Z. You want this distribution to be close to this distribution. And the reason why you want that is so that later on, when you sample from this distribution, it's like sampling from this distribution, which is the distribution that knows about your data. Anyway, I think that's going to be lost on those who didn't understand it. But OK, that's literally redundant. OK, anyway, but so the loss function of this model basically says make your Q, which is called the posterior, like your prior, but also let it reconstruct your data. So put in an image, recode it to some space, and then reproduce that image. That's the name of the game. And this thing maximizes the probability of your data set, essentially. OK, so that's this variational autoencoder model. And you can do this in time, too. So you can have temporal sequences that are optimized, too. And there you get sequences of latent variable Z. So we're going to have a model that produces a prediction about what the next latent variable Z is. And here I've called it a state variable based on all of the previous ones and all of the actions. And then there's a posterior, which also gets to see the actual input perceptual stimulus and produces a kind of an updated latent variable or state variable. This is actually another way of looking at predictive coding. In any case. So this prior is trained to predict the posterior, and the posterior is trained to minimize its deviation from the prior, but it also wants to propagate information about the observation. So at the end of the day, the main thing that you need to take away from this is that you're getting high-dimensional data in, like images, and you're getting out codes that are 200-dimensional or low-dimensional from this, that still are somehow information-preserving and are better shaped. OK, so this has a mechanism. So you now have this sensory data coming in. It's going to be in virtual reality with image, egocentric velocity, the past reward. There's actually a text channel, which is used sometimes, the last action. And that's all encoded by a network here. This is now a feed-forward network. And there's a prior, which is predicting what the next code is going to be, the distribution over it. And there's a posterior, which updates that prior, and then produces a sample of this latent variable, a state variable. So this is a recurrent loop here, and it's producing lots of these state variables that describe the environment. You can use this in two modes. One is you can use it to predict, which we're not going to do, although I can show you a little bit at the end, where you run the prior on its own, and it will confabulate environmental frames. So we had trouble making that work very well, I'll be honest. And it wasn't needed to make the tasks work. You can also use this to just do inference or state estimation to build low-dimensional descriptions of your sensory data that describe enough about the environment to make progress. That's what we care about. So we're building up complexity, and I apologize if that other bit was confusing. But now we're just going to do the same thing, which is, we know how to build RNNs, and now we've built this RNN that's kind of this state estimator system. But now we're going to add a memory to it, so it can store every one of these state variables in memory one by one. And then it can look them up by content-based addressing with keys and produce read values. OK? So this system can now do things like say, I see this painting on the wall. Have I seen any paintings like it before? OK? So this is a twofold advantage building a system like this. One is the state variables are good representations. They're information preserving about the sensory data. And they also help prediction, because if you've stored a lot of stuff that you've seen so far, then you can use that to make predictions. So if I've been over in that room already, I can use that information to predict what I'll see when I go out of into that room. OK? So and this whole system is trained here to decode or predict the image, the egocentric velocity, this R hat thing, which I'll talk about a little bit more, your previous action, just to preserve the information from your sensory data.
So question, is the prediction only dependent, is this just a time prediction, or is this also dependent on the actions?
Yeah, so the prior actually gets the action indirectly, so it's conditioned on the actions. Okay, cool. So this is called the memory-based predictor, and I think that it's something that basically a lot of people have talked about for a long time, I think. So now, instead of doing reinforcement learning in a standard way, what we do is the memory-based predictor is our whole perceptual system. And then the policy is just something that listens to the representations that the memory-based predictor produced. And to prove that, we don't even backpropagate from the policy into this representation Z. Okay? So this is cool. I actually don't like end-to-end learning, and I'd like to get rid of it someday. And this is a case where you can sort of do that. You can produce these perceptual representations that are low-dimensional codes of what you've seen. And then you can just pass them to the policy, and the policy can make do. The policy also reads from the same memory here. That's actually not super critical. Actually, the main thing is that it just gets these Z's. Okay. So now we've just built up stuff. So we've taken all of the work away from reinforcement learning. Reinforcement learning is no longer responsible so much for defining how to perceive or what representations to put in memory. Reinforcement learning is just responsible for tweaking your actions. Okay, so that's what MERLIN is. That's how it works. So you can see it operating on this. This was like a really old experiment of the memory game. And it will sort of jump around. And when it sees something it saw before, it will just go back to it. Okay, and you can do it on fancier images, OmniGlot if you like. And actually, this one has even like random perturbations and rotations to show that it's not exactly template matching when it does it. And here you can see its rollout. So the white thing is where it's looking, and the red thing is where it is most attending to in its memory of locations it had been previously. And to solve this problem, for example, to make one match, to get a point, over here, it sees this thing. As it sees it, it looks up in its memory to the point where it was actually over here, which happened on time step 3. And then on the next time step, it goes back to the thing it had seen and it gets the match. So it's jumping around in memory to be able to find something it saw previously, and then it actually makes the move to that spot. Okay, now there's a bit of a problem with unsupervised learning, which I think people who have played with it know. And I think it's most vividly expressed in the bullet problem. So this is a Space Invaders game. And here's a bullet coming at you, let's say. You're the guy at the bottom. And that bullet is like really small. It's not a lot of pixels. So if you were just to compress data, you'd compress it away. Unfortunately, your life depends on perceiving it. So what do? Yeah, that's a bit of a problem. So we sort of want to compress information, but keep things that are kind of task relevant, goal relevant. And Mark Gluck and Catherine Myers at Rutgers, basically they solved the bullet problem a very long time ago in a paper that was on hippocampal conditioning. So these people doing animal learning experiments. It's really simple. So you could build an autoencoder that takes in stimuli and then produces outputs that are the same and compresses them away. Or you can build an autoencoder that also has to predict something task relevant. In this case, what we're going to do is apply the idea of sort of jointly autoencoding data, but also predicting value or return information. So that's one thing you need to do to, I regret the slide ordering. This is kind of a mistake. Okay, so the other thing you need to do if you want to scale the system up to work on bigger problems is use truncated backpropagation through time. So you can't backpropagate through arbitrary lengths of time. So we're never going to backpropagate through hours, I believe. A simple strategy for dealing with this is you backpropagate only over k steps. Here we set k to be 20, which is roughly 1.3 seconds in our simulation. So the system is only assigning credit over 1.3 second intervals. But you'll see that for memory, that doesn't matter. If you have a robust system that's building memories based on unsupervised prediction, it will just work. Okay, so the thing we've added though in the Gluck and Myers, so these slides should have been the other way around, is we also predict return, even though return isn't in the sensory data, because it's actually a quantity that comes from the future. You have to simultaneously decode all of your sensory data from the compressed state variable z and the return. So you have to make a guess about value. What's going to be the future reward. And that is enough to keep important stuff around. So don't compress away your bullets if they're coming at you. Okay, so then we applied this to problems like navigation. So this is an example of a randomly generated environment. These graphs are boring, but MERLIN works better than the other models. So it has higher score on the top. But the important thing is that it shows memory-dependent behavior. So for example, the first time it goes to the goal, it takes 110 steps. And then the second time, it takes on average 60, and the third time, so on. That means it's learning about its environment. So this is, I should have said, a task where you have to run around, find a goal, and then you're teleported somewhere random in your environment, and you need to get back to it. And it's going back faster and faster each time. Okay, so we can look at all of the representations in the model in the memory-based predictor, what's in the LSTM state, what the read values from memory are, what is in this code, this state variable z. And then we can build a simple linear, or maybe it's an LLP decoder actually in this case, of where you are in the environment allocentrically. And as this thing runs and gets to the goal more and more times, you also get a better representation of where the goal is in the environment. Not where the agent is, but where the goal is in the environment. You can decode that with higher fidelity. Here's what that looks like. So this is what the agent sees at higher res than it sees it. It's exploring for some time. And then it doesn't know anything, so its value predictions are up here. And it sees the goal, and its value spikes up. So it's like, I'm get reward. And then it starts to predict value over here, let's say. So the agent is, you can see, about to turn the corner, and the goal is over there, and it's predicting a rising value as if something good is coming up. So it's learned in memory that this thing is about to come. That's represented here. This agent, MERLIN, can predict, it has lower return prediction error, so it knows things are going to be good many more steps before the goal, the goals are in sight. It has lower error about predicting the actual oncoming value. You can see this on this particular trajectory that the agent's running around, and it's colorizing the amount of future reward it's going to get as something that's more yellow is higher. And even though it hasn't seen the goal over here, it's still expecting more reward to come. Okay. So we can also look at how important this Gluck and Myers trick is, which is to also reconstruct return information along with the sensory stimuli. And for a wide range of values, the system works. So this is how well the system is doing in terms of its score on the game. And this is an exponential scale. So there's kind of a wide range of values of how much you care about decoding reward-based information versus sensory data. This system works. However, there is a sweet spot. And what you can see is that you calculate, so for example, when the goal is in view, you can say what pixels in the image is this reward value sensitive to. So you take the derivative of the return prediction with respect to every pixel in the image, and you sort of say, what's the squared magnitude of that? And that gives you these filters, which pick out exactly where the goals are. It's kind of like a dynamic attention mechanism. I don't want to make claims, but I think that's beautiful. OK, so now you can train another agent that doesn't work with the Gluck and Myers trick. So when you're training your z's, you don't backpropagate from the return prediction, the value prediction. But then you plug on, then you sew them up such that you can backpropagate to run the particular experiment, and this thing is no longer sensitive to the images. So the value is not, it's not a function, it's not sensitive to where the goal is in the same way. Here's the variance explaining analysis is sort of saying you try to regress from the input being the return prediction back to the latent variable z, and more variance in z is explained for higher values of this return coefficient. So if you're asking the system to care more about reward prediction, or return prediction, then more dimensions of z are explained by that. The system automatically develops a kind of hierarchical behavior, which is kind of neat. It's easiest to see here. So this is what kind of, as a scatter plot, where in the environment the maximum read value is of one of the heads that reads memory. And it's all scattered everywhere. It actually basically follows where the agent is. There's another head, though, which is always sort of at the two doors right in front of the goal. And this one is basically even closer to the goal. So as the system is going around, it's reading from memory. If it's been to the goal already, it's reading from memories associated with the entry points to the goal, where the goal is, and right around itself. And you can kind of draw this like spider thing, which is where these heads are kind of maximally attending to in the environment. As you form a memory going around to a place, you can say, where was that memory? And then you can say, which memories are you tending to? And you can map that back to the place. So it got to the goal and see this thing is kind of, sometimes when it's far away from the goal, it's still looking at places near the goal. Obviously, that's just schematic, and I don't expect you to really put much faith into this.
So the lines indicate which memories are recalled at that location. So we see the
So I'm going here, I'm here, and I form a memory at this time point. And then I put it into slot 72. And then I walk over here, and I read from slot 72, and I'm drawing a line from here over to there. This is a visual working memory experiment from Wise and Murray called Arbitrary Visuomotor Mapping. It's actually, in many ways, the simplest of these tasks. But it's kind of related. So you see stimuli, and you remember north, south, east, west. How much more time?
Pretty much out of time.
All right, I'll try to go quickly. I want to get to some cool stuff. So anyway, it learns this task better than humans do. And it transfers to new stimuli sets. Here's one-shot reward valuation. So you go around and eat some objects that are randomly generated, and you know this is good, this one's bad. The system learns after kind of one taste how good an object is, and then it does memory reads back to the events where it was consuming the object the first time. You can see that, but I think as I'm running out of time. Here's a task that is, I just want to talk about it a little bit. It's a block structured task. It's just a bunch of water mazes, and you're going to see the same maze at long intervals between. So if you want to, so this interval between seeing the thing twice is so long that it's beyond our temporal credit assignment mechanisms, beyond backpropagation. But our system, since it's just storing information about the environment locally, is actually able to recall the memories as needed and solve the task. And that literally breaks every gradient-based algorithm we have. Anyway, so you can see that working. But read the paper if you want to. Anyway. So another last one, latent learning. The agent runs around. This one's cool. I just want to show this video, and then everybody can go or something. So there are two doors, and you run around and collect apples as the agent. And there's a top hat over here and a popsicle over here. And you find out what they are. They're valueless in phase 1. In phase 2, you're just doing a distractor task of collecting apples. And then in phase 3, you see in a glass case one of the objects that you were supposed to see before, that you saw before, and then you have to go find it. So this is learning about the environmental structure without reward, and then using it later to solve a task. So here, this is actually not really synced with the top diagram, but it's looking at a TV in phase 3, and it looks back to a time point in memory when it was observing a TV, like over here. And that's how it solves the task. So it does indeed solve this. This is an important principle in animal learning called latent learning, and it can do it to some extent. So let's just watch that because I think it's really cool. So phase 1, collect apples. Phase 2 is nonsense, just do whatever you want. Phase 3, you need to find the thing in the glass box. The apples are needed to make the agent run around, admittedly. So did you see it right here? So it got out of here, it saw the toothbrush, okay? And then it goes and it finds the toothbrush. So that's that. Okay, cool, so that's the end. So we've developed an agent model that can solve, I think, pretty sophisticated tasks in these partially observed environments. The principles are to do perception and memory formation based on predictive modeling compression. Less so than by normal RL. We don't really need to do as much end-to-end gradient computation. So the temporal credit assignment window here was 1.3 seconds, but some of these tasks are 6-minute long tasks. So it can clearly form and reuse memories without difficulty. And it can even exhibit types of learning like latent learning that are not associated with rewards. It can have passive observational exposure to some event or object in the environment and remember that. And what I think is exciting is that it's kind of a functional model of interacting neural systems that really does stuff. It is, we're not, these are really long time scales, six minutes, and it's really getting sensory data that's high dimensional. Thank you.
So in your maze task, does the agent really learn a full map of the entire maze, or is this kind of a collection of allocentric maps of different regions?
I think it's a pastiche. I don't think it really has a cognitive map. I think it really has found some kind of cool strategy for sewing together a bunch of memories of viewpoints into what is needed for navigating. But maybe that's what we do also to some extent. I think that it's really, the jury is still out on how much of a cognitive map we produce.
Yeah, I wanted to ask, in the variational autoencoder model that you have, you can reconstruct the rewards, or the estimated reward. However, if you have a long system where you have sparse rewards, how do you instantiate a reward at that point, even for supervised learning?
Problem, we're working on that, but I don't have an answer for you.
It was obviously not your task or goal to explain our brains, but I'm trying to relate now back to brain computation. And would it be right to say that you aimed at really solving really difficult tasks using, in some sense, neural net-like components as maybe a gold standard or hypothesis generator for how, say, long-term memory could be used for various realistic tasks that the brain has to solve, or how would you phrase it?
So what is the goal in relation to neuroscience? Is that in some sense what you're asking?
No, the question is not, is a workshop about brain computation, theory of brain computation. Where do you see the projection?
So I think it's really important that we come up with existence proofs or models that can produce behaviors that are like what brains can produce. To have at least some hanging around, and then we can, do hypothesis testing. So, yeah, I would like to have the processes of the brain, the functional outcomes that the brain produces be less mysterious, and then we can do things like train animals on tasks and train our agents on tasks and see if the behavior matches up. We can look for actual circuitry that's correlated, but I think to do that, you need to first make sure that the behaviors are actually working right.
So is there any quantification, analytical or otherwise, that is of the improvement brought about by the MERLIN?
So
Is there any quantification, analytical or otherwise, of the improvement that is brought about by having the memory?
Right, so there were the knockout experiments that I didn't show, where you knock the memory out and you can show that it doesn't work. You can do that after training, which is obviously very deleterious, or you can do that while training and then it doesn't work. I showed you related models like the RLLSTM that don't work. So they're all experimental results, I guess, but that's where we are.
And another one. You're getting very close to model-based RL here, right? But you yourself said if you use the thing for prediction, it doesn't work. Is that also due to the traditional problem of compounding errors, or was there some other problem yet? And the second question I had is, you said you're very happy that you can train these modules separately, the decision-making module in some sense and the perception module with the memory, and that's cool. Could you also train them jointly?
Mm-hmm. Yeah, you can train them jointly and you get no added bonus, so nothing, doesn't matter. We have that experiment in the paper. Why does the model-based rollout now work? It does work for like a step, but what do you want to do with that? So it's actually kind of my motto coming in was, what can we do with crappy models? I've always felt that way because we're never going to have really great models. I just don't think it's possible, especially in partially observed cases. So I'm kind of ecstatic that it does anything at all. And you get a new kind of model, which is a model in memory. So there's a bunch of stuff in memory that can be queried and so on, and that tells you as much as you need to know about your environment historically. And the system learns, based on trial performance, what to care about in its model. So I'm more excited about that. Now, do I think it's not a good idea to continue to improve the model and see where you can go? I think it would be a good idea to do that. There are technical things we can do, building better posteriors, non-Gaussian posterior, people, all the stuff that people geek out on VAEs do. And also different kinds of models I think would be exciting. And indeed, I don't know, should we do things like Dyna or simulated rollouts in memory space? I think there are some problems where you really do want to do stuff like that. So we're playing around with things like that. We don't have it in very simple games. Like this memory game was really important for us intellectually. Like it seems like a trivial problem, but we really figured out that other models can't work on it, and that was important to give us faith. And we're doing like puzzle games with sort of imaginative planning and stuff a little bit too. So, but I don't know. I don't know if I really want to work so much on making this model that much better, but I think people will do it, and I think that's a good thing to do.